Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Lorenz Roth, who's come across to us from Southwest Research Institute in San Antonio. Lorenz did his MS or diploma at University of Cologne and a PhD at the same institute in geophysics. The topic of his thesis was observations of Jupiter's Galilean satellites. He is interested in thin atmospheres and on these satellites, observations and models of the satellites, including interiors, atmospheres, and surfaces of the Galilean satellites, and simulation of Io's auroral emission, and observations using Hubble Space Telescope, the New Horizons spacecraft, and also the Galileo spacecraft. He is also published on observations of Europa's UV emission, and most recently, and the topic of his talk today, is looking at transient water from the South Pole of Europa using Hubble Space Telescope. So please join me in welcoming Lorenz.
Yeah, thank you very much for the invitation. I'm very glad to be here and present our research with the pretty exciting latest results of the discovery of water vapor at Europa. And first I want to thank my collaborators who are listed here below. They really helped me a lot in this project and kind of guided me through this sometimes delicate subject, and that's I really want to appreciate at this point. So the title of my talk, Water Vapor at Europa's South Pole, Observations by the Hubble Space Telescope, has kind of two parts. The first part, water vapor at the South Pole, is kind of depicted here in the background image with Jupiter in the back, and then Europa, and then kind of water vapor ejected somewhere near the South Pole. And the second part, observations by the Hubble Space Telescope, that's the images here, the blue grainy images. These are actual observations by the Hubble Space Telescope. And today I'm going to try to explain why these bright pixels in the encircled area here at the South Pole indicate that water vapor plumes like the one depicted here exist at Europa. A short outline of my talk, very simple. Today I'm going to speak first about Europa. I'm going to introduce the moon and say what's so special about Europa, why Europa is so interesting, in particular in astrobiological aspects, and then I'm going to come to the observations we use to study Europa, and we use Hubble Space Telescope observations, as the title already said, to look at ultraviolet emissions from the atmosphere of Europa. And that leads to the images, to the Hubble Space Telescope images that revealed the detection of water vapor. And in the end, I'm going to briefly speak about what implication this detection of water vapor has on future Europa exploration. So this is a family portrait here of the 4 large moons of Jupiter from the left to the right, and that's innermost to outermost, Io, Europa, Ganymede, and Callisto. And in planetary science, we always like to compare principally to find out if a phenomenon is universal or more unique for that we find at a certain body or point in the solar system universe. And this is of course very practical to have in one planetary system, in the system of Jupiter, 4 large moons that do have similarities that we can compare, but also have differences that make clear that something is really unique to one of these moons, and there are uniqueness features at Europa. At the bottom, another comparison, the Earth-Moon, just to kind of show the size or to get an idea about the size of the moons of Jupiter. So Io is very similar to the Earth-Moon. Europa is a little bit smaller. Ganymede and Callisto are about 50% bigger than the Moon. And there is a very or comparatively small moon of Jupiter, of Saturn, Enceladus here. And although this moon is really small compared to the other 5 here, Cassini spacecraft showed that active plumes are ongoing at the south pole of this small moon. And of course, when speaking about plume activity at Europa, a comparison with a well-observed plume active moon, Enceladus, is very useful. Let's have a look at the environment of the 4 moons. That's Jupiter in the middle with its magnetic field here, the blue lines, and the dipole moment of Jupiter is slightly inclined with respect to the rotational axis, so the orbital plane or the equatorial plane of the magnetic field is also tilted with respect to the orbital plane of the moons, and at the same time Jupiter rotates much faster than the moon's orbit Jupiter, so the environment is changing on a 10-hour time scale of the moons, and the orbital periods are on the order of days. So all moons orbit Jupiter in a highly variable plasma environment, and the red diffuse glow here shows the Io plasma torus. So there's a dense plasma that rotates with the magnetic field in this 10-hour period and overtakes the moon constantly. But let's zoom into Europa. We know from gravity measurements that Europa is a differentiated body, taking the normalized moment of inertia here that we know from these Doppler gravity measurements from Galileo. This is 0.346, and whenever the normalized moment of inertia is smaller than 0.4 of a sphere or of a sphere-like body, we know that the mass is more concentrated toward the center of the body. So the higher density is in the center here, an iron or iron-sulfur core. Then we have a silicate mantle, and the outermost layer is the least dense layer, that's H2O. The thickness is about 80 to 170 kilometers. We know that the surface is frozen, but below the surface there might be liquid water, but this is not clear from the gravity measurements. The water or ice makes up about 10% of the total mass of Europa. Europa also has a very tenuous atmosphere with a surface pressure on the order of 10 to the power of minus 10 compared to the surface pressure here at Earth, so really tenuous. That's why it's often also called an exosphere, because the particles can propagate almost collisionless. Europa orbits Jupiter on an eccentric orbit, and the reason why this eccentricity is kept up is the so-called Laplace resonance with the neighboring moons Io and Ganymede. So that's the sketch here. To the lower left, whenever Ganymede orbits Jupiter once, Europa does it twice and Io 4 times. And this leads to the fact that from time to time they are aligned like they are here in the sketch, and this alignment, kind of this pull from this alignment, keeps up the orbital eccentricity in case of Europa, but also Io and Ganymede. The rotation is also tidally locked, meaning that the same hemisphere faces not towards Jupiter, but towards the center of mass. And since Jupiter is not always in the center of mass of the system, the moon librates. And this libration and the variable distance, absolute distance of Europa from Jupiter, kind of leads to changing absolute gravitational pull, and also the change of the direction of the gravitational pull, which kind of needs the moon constantly, and this tidal deformation gets dissipated and creates energy, tidal heating in the interior of Europa. And this tidal energy leads to a wide range of interesting and also observable features on the surface of Europa, but might also be able to keep the water from freezing inside Europa, and potentially also drives activity at Europa. Here are a couple of these interesting surface features. There's, for example, these so-called lenticulae, kind of freckles that zoom in here to the bottom left. You can see that it looks like domes, and it's thought to come from warm material that rises up from below. Then you have replenished craters, or these cycloidal features to the lower right here that are generated also through the tidal variation in one part of the orbit, the tides kind of exert tension on the cracks on Europa's surface and can open the cracks. And in that part of the orbit, there's a relative movement between the two sides of the cracks. And in the other part of the orbit, there's compression exerted on these fractures that kind of puts them together, and no movement can take place anymore. And this creates this very special cycloidal features on the surface of Europa. We also have chaos terrains, like the Galileo image here in the upper left, with ice blocks that seem to be tilted and displaced, shifted from their original position. And these terrains could be pretty well explained by lake models, so a pretty shallow local lake below the frozen surface, and these ice blocks break apart and tilt over and move around, floating on this lake. But all the geological evidence is not sufficient to distinguish between two interior models that are shown here to the right. So we have either in the upper part of the right image a really frozen solid outermost shell, and then warmer convective ice below that could explain a lot of these features, maybe together with localized lakes. And the other possibility is that we have a global ocean, so really below the solid surface, liquid water all over Europa that is actually connected. But an additional measurement kind of allows us to distinguish between these two cases, and that's the magnetometer measurements that were taken by the Galileo spacecraft. The sketch here at the top shows again the magnetosphere, and the magnetic moment of Jupiter, as I said, is tilted by about 10 degrees to the rotational axis, and that leads to changing orientation and amplitude of the magnetic field at Europa. And I'm going to start a movie now, hopefully. There it goes. And if you look at the yellow line here, that's the magnetic field line of Jupiter crossing Europa. It's changing direction constantly at Europa, and such time variable magnetic fields can induce currents in an electrically conductive layer or in an electrically conductive body. So the iron core could be conductive, but that's far away from the surface, and it's hard to measure induction signals from an iron core. The solid frozen ice has hardly any conductivity, but liquid, salty liquid water has a conductivity that is sufficient that currents and then secondary magnetic fields are induced in the interior that can be and are actually measured by the Galileo spacecraft. That's shown here to the lower right. Such a dipole field is induced in the interior and could be measured during several flybys of the Galileo spacecraft. So that kind of gives us confidence that the liquid water actually exists today and also is global. That the global ocean is needed to create these induction signals. Now I'm going to use a comparison again to kind of point out why Europa's ocean and Europa is special also compared to the other four moons. We have Io. Io is known for its very active volcanism. Io has over 100 active regions, and you see huge gas volcanoes that are also driven by tidal forces. And Io has lost all its water, so there's no water anymore, but you see a lot of activity. Going out to Ganymede and Callisto, both moons are also thought to have global water oceans. Evidence comes from the same method of induction signals, but in the case of Ganymede and Callisto, we think that these liquid layers might be sandwiched between two layers of frozen ice. Whereas at Europa, the liquid layer, I mean, it's hard to see here, but is thought to be connected directly to the mantle. So we have the bottom of the ocean connects to the mantle of Europa and is not isolated through another layer of ice like in Ganymede and Callisto. And speaking of activity, so if we go out to Ganymede and Callisto, we see a lot more craters on the surface. So the resurfacing processes are lower. There seems to be a lower activity. The tidal forces are less strong than at Europa and Io. And so Europa might be right in the middle between the very active Io and the very icy moons, Ganymede and Callisto. And this position makes Europa maybe the most promising candidate for a habitable environment in the solar system. So we do have water, important solvent, a relatively warm, salty H2O ocean, which is global. We might have the essential elements, accretion from impactors, so impacting comets might have delivered the essential carbohydrates, organic elements that probably can make it through the ice into the ocean. We do see hints that there's exchange processes between the liquid ocean and the surface. Although radiation can destroy organics in the very uppermost part of the solid ice, they might still be able to reach the surface. We also do have chemical energy at the top of the ocean, radiation. The same radiation can create oxidants, and even more interesting, due to the direct contact of the ocean with the mantle, we might have hydrothermal activity, and at these hydrothermal vents, they provide a habitable environment. We know that from Earth, and create this chemical disequilibrium that is necessary that we think is necessary to allow life to evolve. And these three things, water, elements, and chemical energy, are also sustained over a longer time period. So a relatively large body like Europa can sustain this environment over a longer period, which really allows life to evolve over a longer time in several steps. A lot of this is still assumptions and nothing, I mean, the water, the ocean, we're pretty sure it exists, but nothing else has been proven yet. So it would be highly interesting if we could probe this subsurface world, if we could get there and really see what's going on down there in Europa's ocean. It's of course hard to land there, to drill into the surface, all these things. But what if we have, like at Enceladus, the little moon of Saturn, active outgassing? So that's images from the Cassini spacecraft that really nicely show these continuously active plumes at Enceladus to the left. And something similar has not yet been imaged at Europa, but of course it might provide the outstanding opportunity to really probe the native composition of Europa. To really, if the plumes are connected to the liquid ocean, we could also potentially probe the ocean by just, and I said that in comparison to landing, just flying a spacecraft through a plume like this. So is Europa active? It's highly speculated, and there have been a lot of considerations, and also people thought they have seen something in images from the Voyager spacecraft or Galileo, and for these Galileo and Voyager images, there has been one kind of concluding analysis that they really looked closely, Cynthia Phillip and colleagues, at all these images and could not detect any limb haze, like in the left image here that shows the limb of Europa and something above the limb, which was thought to be a haze coming from activity, but it turned out it was just a ghost image, much fainter than the actual image and displaced by a couple of pixels to the right. And also they compared like images from the two spacecraft, Voyager and Galileo, of the same surface areas and could not find any suspicious changes between the Voyager images and the Galileo images. So it all looked like Europa might still be active, but maybe we're not able to see this activity with the images and possibilities we have so far. And then I come to our approach of probing Europa's neutral gas environment, and also in that sense plumes, like local neutral gas environment inhomogeneities. We use auroral emissions, and in particular we use observations by the Hubble Space Telescope to observe these auroral emissions from Europa. I've mentioned it in the beginning, Europa does have a tenuous atmosphere that consists mostly of molecular oxygen, and the detection of this molecular oxygen atmosphere has been already achieved with such UV observations, and it's the spectrum here to the left. That's a UV spectrum, so the brightness, the measured brightness as a function of the wavelength here between 130 and 140 nanometers roughly, and you see two emission peaks here at two wavelengths, and these are two oxygen emissions at 1356 and 1304, and the relative brightness of these two peaks is about 2, tells us that the process that's going on here is electrons from the plasma environment of the moon, electrons from Jupiter's magnetosphere hit the atmosphere, the molecular oxygen in the atmosphere of Europa, dissociate it and excite it, and then finally these emissions are generated. So that's the spectrum finally brought evidence for this O2 atmosphere, and the sketch to the right kind of illustrates first the generation of the atmosphere that is sputter generated, so the green circles show the gyration of the ions of the magnetospheric environment around the magnetic field line here, and when the ions, high energetic ions, hit the surface, they break the water apart in the surface and kick the molecules out, or the atoms, oxygen and hydrogen, and the electrons here, the smaller circles, also then hit the newly generated O2 atmosphere and generate the observed auroral emissions. A couple of years later, the first images were taken of these auroral emissions by the Space Telescope imaging spectrograph, another camera on Hubble, and the image is shown here to the right. The left is upper right, and the left is a simulation of these auroral emissions, and surprisingly we saw a pretty irregular emission pattern. So it's definitely brightest here in the northern right quadrant of the disk, and from simulations you expect a relatively similar limb glow as you see in the left image here. So you expect the aurora to be brightest just at the limb of the moon, because the line of sight through the atmosphere is longest from the observer at the limb, so the column density of atmosphere you look through is highest. So what in principle can cause such an irregular emission pattern here as observed in the first observations or first images taken in 1999? In principle, it can be, of course, either the electrons that hit the molecular oxygen that are kind of unevenly distributed and excite more emission in the upper right part, or of course it can be the atmosphere itself, that you find more O2 molecules in this case at one part of Europa and have a brighter auroral emission there. So that kind of these observations kind of brought up the idea that you can probe the atmospheric distribution with aurora observations. In a follow-up observing campaign with a different camera on Hubble, HST ACS, the advanced camera for surveys, which had to be used because the original camera STIS was not in order at that time. We tried to, or a group tried to kind of follow up this idea, took new observations at different positions of Europa, but it turned out that the data quality of these observations did not allow to draw conclusions. You see here the image to the lower left, all the bright signal here in the right part is artifacts, and you cannot really tell what's going on. Still, an analysis of the data showed some hints of plumes and brought up for the first time the idea that you can connect such emission asymmetries with potentially active regions of Europa's surface. Thence the Space Telescope imaging spectrograph was repaired during the last service mission of the Space Shuttle to the Hubble Space Telescope, so we was available suddenly again, which was good for us because we could take these original measurements again from 1999, and here is a sketch of the observation setup. So it's imaging spectroscopy, meaning the slit, you see here to the left, is wider than the disk of Io or Europa in this case. So you have the moon, the entire moon in the slit, and disperse the light along the horizontal axis, and you get then kind of monochromatic images for each wavelength, where you have either emission or reflection along the so-called trace here of the moon along the horizontal axis. This is an example image taken by STIS in November 2012. The upper part shows a cut from the detector where the trace of Europa is, and we are now interested in 3 wavelengths or 3 colors. One is the hydrogen Lyman alpha line, and the 2 oxygen lines I mentioned earlier that were used to detect the O2 atmosphere. So we have 3 images, we take out 3 images in one such spectral image and look at them closer. The bottom panel shows the spectrum that is generated from this spectral image. So you integrate along the vertical axis and kind of lose the spatial information, and then you have only information of the brightness as a function of the wavelength. And what we did then is we wanted to separate light that is just sunlight reflected from the surface from emissions that are really coming from Europa or Europa's atmosphere. So at longer wavelength, you only see reflected light, and we modeled this reflected light and adjusted the brightness to the observed brightness here, and that's the dotted line in the graph below here, the model for the surface reflected contribution to the image or to the spectrum. And you see that the albedo is on the order of 1.5% here, and compared to the albedo of Europa at visible wavelength, which is about 60%, this is really low. So the surface reflected light is really, really low at UV wavelength here, and that's the advantage of these UV aurora observations. You can hardly do these observations at visible wavelength because the reflected sunlight would be so bright, you couldn't hardly figure out what auroral emissions you see in your images. And that's also important because Hubble is kind of the last telescope or space telescope that can do these UV observations, and the successor, the James Webb Telescope, for example, will not be able to observe in the UV, and so we're glad as, for every year Hubble continues and we can use it to do these UV observations. Comparing now the modeled surface reflected light here in dotted red with the spectrum in black, you see that at the 2 oxygen lines there's a strong emission from the atmosphere of Europa, so the black lines are higher than the dotted red lines, whereas at the hydrogen Lyman alpha line the black curve and the red curve match very well, meaning that most of the light we detected, we observe here, is just surface reflected light at the hydrogen Lyman alpha line. And we have images, these kind of spectral images, where we take out the 3 monochromatic images taken on 3 dates so far. So there were 3 so-called visits of Hubble to Europa, where we observed with this setup. One was in October 99, the other one was in November 2012, and then we had one in December 2012. And the sketch here shows Europa's position in its orbit around Jupiter with respect to epicenter or pericenter. And in October 99, Europa was pretty much at pericenter, so at the closest point in its eccentric orbit to Jupiter. Then in November, a bit earlier in its orbit, but also pretty close to Jupiter, in December 2012, Europa was instead far away from Jupiter and more or less or shortly after epicenter here. And this will be important later. But we do have now 3 dates, so 3 observations, and in each observation we have the 3 images, the hydrogen Lyman alpha line and the 2 oxygen images. So it's 9 images. Then I come to the last part of my talk, which I start with these 9 images. And so the columns are the 3 visits, and the first row is the hydrogen line, the second row is the first oxygen line, or the 1304 line, and the third row is the 1356 emission. And like I said, at the hydrogen line, the images here show the light after we have subtracted everything that is reflected from the surface. So it shows only emission from Europa's environment or atmosphere. And as we have seen in the spectrum, when we subtract the surface reflected light at the hydrogen line, there's not much left. So these blue pixels are all probably statistical fluctuations, and adding up, it's a 0 emission. But surprisingly, then in December 2012, after we have subtracted the surface reflected light, we have a bright 500 Rayleighs. Rayleighs is the units here. The photons per square meter per second are measured above the South Pole here. And looking at the oxygen images then, you see a lot of emissions. Most of them are coming from the global O2 atmosphere. You won't see the O2 in the hydrogen lines, just because there's no hydrogen in O2. But most of the oxygen emissions come from the global O2 atmosphere. But interestingly, looking at the 1304 emission from December 2012, you see in the same area here near the South Pole, where the hydrogen emission surplus is detected, a small but still observable emission surplus at the first oxygen line here. So we have 500 Rayleighs hydrogen emission surplus, about 25 Rayleighs oxygen emission surplus, and looking at the other oxygen line, it's brighter overall, but looking closely above the limb, we do not see a local surplus in this oxygen emission. And the combination of these brightnesses and the non-detection at the 1356 line is exactly consistent with what we expected for electron impact on H2O. So if we have a localized H2O abundance that gets dissociated and excited by the incoming electrons, we would produce hydrogen Lyman alpha and oxygen 1304 with a ratio of 20:1, but relatively little oxygen 1356, so in this case not detectable. And so that was our conclusion, that the most viable and only possible process is really that we have a local H2O abundance in this area to create these emission surpluses. Another interesting hint was that if we look at the evolvement over time, so we have the image from December, if we cut these images in 5 time steps, the first row is the hydrogen image, so 5 time steps from the beginning to the end of this visit in December 2012, and the second row is the oxygen emission in 5 time steps. We do see, although these images are really patchy and really noisy because of a low signal to noise, we do see some emission in this encircled area here at the South Pole, indicating that this is really spatially persistent. We see this as the same location on Europa, so it's always at the South Pole, whereas other emissions, looking only at the other oxygen line that is not affected by the H2O, we see a variability and a changing over time within the 7-hour period. So the persistency here, in addition, indicates an atmospheric inhomogeneity. What we did now is we tried to model, with a relatively simple model, the excitation of the auroral emissions and compare these model images to the observations. So the left column is the 2 observations and the right column is a model. We assume a homogeneous plasma environment, so homogeneous electron density, temperature, and these electrons come in, they excite the atmosphere. We assume a global O2 atmosphere that's everywhere around Europa, and then we put in 2 localized abundances of H2O, of water, and also excite these localized H2O plumes. And it turned out that the best model case was like if you put in two about 200 kilometer high and 250 kilometer wide water vapor plumes with column densities on the order of here 10 to the 20 H2O molecules per square meter, we get the best agreement. And the quantitative comparison is done by comparing these limb areas here. We have these yellow dotted sections around the limb of Europa, numbered from 1 to 18, and these refer to the data points here in the right plot, and you see the clear emission surplus here in the first panel to the right at the hydrogen line, and then in the second line the same limb bins is also an emission surplus, and again the model is here in dotted red, and we got the best comparisons for two plumes that are about 200 kilometer high. So, but why did we not see, assuming that this is a constant phenomenon, that the electron environment is kind of constant, why did we not see it early on when we looked in October 99 and November 2012? These are the exact same images, the viewing perspective changes a little bit, and maybe the plasma environment also, but the signal is pretty clear, so we would expect to see a similar signal if these plumes were there in the same way all the time. And to the right you see the sketch again of Europa's position in its orbit around Jupiter. So like I said, in December Europa was at epicenter far away from Jupiter. In October 99 and November 2012 Europa was closer to pericenter, closer to Jupiter. And looking now at the tidal stresses that are exerted on the surface fractures of the South Pole, that's what the plots below show. So that's a view onto the South Pole. The South Pole is in the middle, and these dots here, white, brown or black dots, show the fractures that you find all over Europa's surface in a digitized way. And when the dots are white, that means that there's no tension exerted on these fractures. When the dots are brown, there's little tension, and black dots mean that tension is high in this phase of the orbit. And it turns out that really in October 99 and November 2012, these fractures are actually in compression, or not in tension at least. And in December 2012, we see tension at a large area here, and this tension potentially opens the cracks and lets the water vapor to escape and allows the detection here only in December 2012. This is of course a pretty weak statistics, 3 data points, and then deriving an universal behavior, and that's why it's so far more like a suggestion. Interestingly, just last year, very similar variability has been found at Saturn's moon Enceladus, and you see here again a sketch. It's the orbit of Enceladus around Saturn, and left is epicenter, right is pericenter, and looking here at these images taken by the visible and infrared mapping spectrograph of Cassini, black pixels are the moon, the bright pixels to the right are kind of the rising sun, and the bright pixels below the black pixels are show the plume activity, and you can see that here at epicenter the plumes of Enceladus are more active than at pericenter, and this really has been observed many times throughout the orbit, so we really have a consistent behavior of kind of breathing, more activity and less activity with the orbital position of Enceladus. So a similar behavior could take place at Europa. It's just not, you cannot say it with 3 data points so far. So finally I'll speak about possible implications. So we might have now with these plumes, if they are connected to an ocean, we might have access to Europa's subsurface, potentially habitable world. And NASA has plans for many, many years to go to Europa, because Europa is so interesting, and there has been plans for about $4.7 billion mission, but these have been rejected as just too expensive. So the next goal was to find a good science mission that keeps the budget within $2 billion to go to Europa and explore Europa and its habitability. And several mission concepts have been put forward, either an orbiter that flies Jupiter, then goes into orbit around Europa and orbits Europa for a longer time, or you can have a lander even, so you land on Europa, take samples from the surface, which turns out to be just too expensive to achieve any useful science. And the third option was an orbiter, was a flyby mission, so you fly to Jupiter but do not orbit Europa, but Jupiter all the time, and then have several flybys at Europa and do science then. And the reason why an orbiter is kind of hard to achieve is the harsh radiation environment at Europa. So if you stay with Europa all the time, the radiation environment is really harsh all the time, whereas a Jupiter orbiter with just flybys at Europa can fly out and come back all the time to Europa. And the plume discovery, I often heard the word game changer, and I'm not sure in the end if it really changes any game. What happened this year was that NASA said, yeah, well, $2 billion, we might not be able to provide this $2 billion, so they asked for, they put out a request for information for an even reduced cost mission to Europa within $1 billion, but there's no results out yet. Just today, NASA put out another opportunity notice for now instruments, getting closer for a mission to Europa. And the mission that's mostly in discussion so far is the Europa Clipper, defined by a science definition team, and the earliest launch might be already in 2022, which is not that far in the future, I think. And there are considerations using the new space launch system. We could go to Jupiter in less than 3 years, meaning that we could be there like in 2025, a little over 10 years. Sounds pretty exciting to me. And the possibility then to fly through a plume and really measure the native composition of Europa or its ocean would be, of course, very exciting. The thing is only, we definitely need confirmation. As long as we don't know where exactly these plumes are, when they occur, it's going to be hard to have a mission like this one here, 45 flybys, and then be exactly at the right time, at the right position to fly through the plume and measure it with a neutral mass spectrometer, for example, and find out its composition of the plume. So in summary, Europa is very interesting. It has this subsurface ocean that potentially provides all ingredients for life. Hubble Space Telescope observations taken in December 2012 have now for the first time revealed indications for the existence of water vapor plumes near the South Pole. I've shown here the area like in the lower right here. That's the middle of the image is kind of where the plumes, at least derived from these two-dimensional Hubble images, are coming from. And so far we do not see any surface features there that indicate the existence of such large plumes. And this plume activity might provide the unique opportunity to really probe Europa's native composition, probe the habitable environment, but it's really essential now to confirm it, where these plumes are, when they occur, to kind of follow this track. Thank you.
Okay, if you have any questions for Lorenz, put your hand up and I'll get around to you. So Lorenz, I have the first question. So what can we do for confirmation now? And then you mentioned that NASA has now put out a call for instrument proposals. Mm-hmm. Is there a potential for UV spectrometry to be proposed there? Can you talk to us a little bit more about that?
Yeah. So in principle, what you can do, I mean, what we already did, it's not yet published, but we tried already to repeat these observations, kind of the same constellation of the detection, and we did not see any signs like we saw here in December 2012. So it kind of looks like it's not as simple periodic as you might think, with like an epicenter, they're going off and then they disappear. And there's also plans, so we want to do more observations just over a longer time period and in different orbital positions of the same kind here, to kind of try to understand the variability and the cycle, or just to be lucky again, I guess. And for the Europa mission, they're like in this so-called strawman payload. So in the so far proposed payload, there's no UV instrument included. It's more focused, or it's focused on like close flybys and really doing good science when during the flyby section that is indicated here in this sketch. So you have an ice penetrating radar that really tries to sift out where's the water in the ice, and thermal imager to find thermal anomalies, and topographic imators to kind of analyze these interesting surface features. A UV instrument, from my point of view, would be, of course, a nice addition, just because it is capable of observing plumes, as we have shown, and it also is so like from remote sensing. We don't need to be at Europa, we can be pretty far away. I mean, we have probably a spacecraft that orbits Jupiter and comes back to Europa all the time, and we can look from further away. We can scan the limb, for example, and look for any anomalies with these UV spectra and images. So I think it's a good addition.
I have read that the ice on Jupiter contains hydrogen peroxide. Is this a surface phenomenon, or would you expect this to occur also in deeper layers?
As far as I know, the best explanation for the hydrogen peroxide is that it's coming from deeper layers, and actually coming from below and diffusing to the surface, kind of giving hints for such an exchange process between ocean and upper layer. And it's not exterior or exogenic, but endogenic.
Question here. If the plume is real, and if it has the number density you are estimating, and if you had a spacecraft flying through it, you talk about confirmation, you could confirm the water, but would the mass spectrometer have the capability to make interesting observations of trace constituents at those number densities?
Just using a comparison again to Enceladus, this number density we derived, like this is a rough number still for Europa with the one observation, is very similar to what we see at the Enceladus plume. And just assuming that the composition is also very similar, and comparing it or using the results from the Cassini mass spectrometer, we could constrain the abundance of methane, of other constituents. To what number exactly, I don't know, but in the same. Yeah, I think, I mean, for Enceladus, we do know a lot in part from these neutral mass spectrometer measurements.
So just in case anyone's interested, the call for instruments, so the announcement of opportunity for the Europa mission from NASA came out today. So if any of you have a great instrument concept, you go look on the NASA website, you can find out all about it. And they did actually, in response to this this great discovery of the plumes on Europa, they did add to the potential payload, so the strawman payload, they added a in situ plume science instrument, so something that would actually sample the composition of the plume flying through it. So that is in the list of potential instruments. There is also, for any of you guys who are on Reddit, there was an Ask Me Anything from a couple of the top Europa scientists this morning. So you can go and read the archive. There's some great questions and answers on there.
Hi, this is actually off your main point, but early in the talk you made reference to the possibility of convective ice, and I'm trying to wrap my brain around how that would function.
What convective ice is?
Convective ice.
Yeah, you warm. Yeah, it's warm ice that like allows like for the tidal stresses to allow some kind of movement. I mean, if you increase the temperature of ice, you kind of reduce its word is missing. Yes, the tidal forces and like a not completely solid ice body, but warm, movable ice.
Okay, thank you.
Yeah, over here. Hi. So given that you have a lot of observations of Enceladus, and while you're waiting for the ability to get more observations of Europa, is there a model that either your team or the Enceladus team is working on that you could then, you know, to match the observations of Enceladus plumes, that you could tweak to predict better the plumes from Europa?
Yeah, it's most difficult mostly because even the one detection is kind of it's hard to constrain the location, the where it comes from, the source location, then even the abundance, the amount of water there, and like yeah, the statistics, 3 dates, one detection. There's just so much flexibility that does not really allow to really model this. So you can model this, and then potentially there could be open cracks all over the surface and small plumes everywhere, but it's just hard to say where they exactly are, where they can occur, when, and with the little constraints we have so far.
So I have a question about whether you and Cynthia can jointly read the minds of NASA headquarters. And is the story on Europa going to be that we're going to have to do a plume flyby mission before they think about actually implementing a surface mission and any other way of accessing the oceans?
Yeah, I mean, I basically agree that one has to be cautious about, for example, converting this mission concept into a plume mission is really risky at this point with the lack of confirmation of the plumes. So, but if we knew, I mean, if there is confirmation, and I mean, there's a lot of people working on it, so I kind of could expect that every day is someone calling me and saying, hey, we found it. Then I would definitely think we should first do this, because it's just, so from the cost point of view, it's so much less money to fly through a plume and do good science than to land there and take samples. And we anyway need this exploration mission in preparation for a potential lander, I think, to kind of sift out the surface and find an area where we could land or where it's interesting to land. So that's definitely the next step. So, and not the lander and what I think. I don't know, Cynthia.
Yeah. Assuming you do find and actually verify these plumes, would it be realistic to assume that, okay, if there's anything like a microbe living down there anywhere, that they would be spewed out by these plumes and therefore could be detected possibly? And do we have flyable hardware that could actually do that?
Yeah, that's, I mean, the first thing, if there's anywhere a microbe, what's the probability that it's spit out exactly there where the plumes are? I don't know, hard to say, and there's a lot of uncertainties in there. And we always have to take the next step. So, I mean, if we sample a plume and find carbohydrates, anything, that would be already a big step. So if we know anything about the native composition, we would come closer. I think it's premature to kind of be so optimistic, or it's too optimistic to say we fly there and really find evidence for life. So that's not going to be the next mission, I would say.
Okay, if you have any more questions for Lorenz, I encourage you to come up and also have a look at the Europa globe here. Lorenz, we have a special mug here. It's a SETI Talks mug. Looks like you'll have many hours of coffee-induced
I will.
thinking to be done about the plumes here that you've discussed. So please enjoy it wisely. Please join me in thanking Lorenz for a great talk.
Thank you.